Hello everyone and welcome to the next session of our Digital Redays. My name is Silas and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today is Don't Let EMI Ruin Your Day, Shielding New Challenges. Our speaker today is Victor Martinez, who is working as a product manager at Würth Elektronik eiSos. Before we start with the webinar, I would like to give you some more information. First of all, you will be muted during the webinar. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions via the chat function. Today's webinar will be about 30 minutes long, and after that we will make a live Q&A session, and then Victor will answer your questions. If we are unable to answer all your questions live within this time, Victor will answer them via email in the next days. So, last information from my side, you will all receive the link to the presentation as well as to the recording in the next days via email. So now I will hand over to Victor and I wish an exciting webinar.
Hi to all, my name is Victor Martinez. I'm a product manager from the Shielding and Thermal team, and today I'm going to be the speaker for the session Don't Let EMI Ruin Your Day, Shielding New Challenges. The agenda for the session of today will be to give a quick introduction about why shielding materials are needed, and then I will jump directly into the topic for giving tips about how to use properly the different shielding materials that are available on the market, including among them EMC gasket, more level shielding, and also magnetic absorbers. At the beginning, about why shielding materials are needed. So we have electromagnetic fields in the outside in the environment that may affect or will provoke some problems into our applications, like our mobile phones, laptop, maybe the TV, or even the cars, especially jumping into the automotive sector. And then those electromagnetic fields, they could provoke some noises and resonances into the systems from the applications, which at the end can provoke some errors and malfunctions. At the end, also, all of those electromagnetic fields are being radiated for anything metallic that has a current going through it. So then that means that anything can be an antenna, including, for example, some cables, some input-output interfaces, some apertures, like, for example, from the frame and the cover of your application. Also into the PCB, we will have some traces and ground planes that can be also a good antenna that could provoke some electromagnetic fields. And then also some passive components, like, for example, a heatsink in this case. Then we know that on the market there are several ways, or there are several types of shielding materials, and all of them, they have different properties, and also they are made in different ways. So then the best way to compare them, it is with the use of the shielding effectiveness, which at the end it is a quantitative property, which at the end gives you the value about how much is the material attenuating, or it is like removing the field in the environment. So at the end, this is a really simple measurement, because what is being measured is the environment without the material, without the shielding material, and then you just place the material into the middle, as you can see here. And then, so in this case, this will be the material, and then you just make one value minus the other one, so then you get at the end the shielding effectiveness. Then some rule of thumbs that will help you out to more or less identify which product you need to use or which type of shielding material you need to use is that, for example, if you want to attenuate or you want to shield your device from an electric field, then what you need to use, it is a low impedance material. In this case, it can be, for example, a copper tape or an aluminum tape. Because at the end, what you want to have, it is a high conductivity material. And then if it is the other way around, that you want to attenuate or you want to shield your application from a magnetic field, in this case, what you need to use, it is a high permeability material. So in this case, it has to be, for example, a ferrite sheet. Then also another rule of thumb is that normally, if you want to attenuate, in this case, a magnetic field, normally the thicker the material, the more that it will attenuate in this case, especially speaking about ferrite sheets. And now jumping directly to some tips here that probably they will be quite useful for you. For example, EMC gaskets, where they can be found, where can you use them, or where can you see them? At the end, EMC gaskets they can be found everywhere. If you have an enclosure, then probably you're going to have a gasket over there. So as you can see here, for example, on this device that we have a heatsink and everything, that we have an enclosure. As you can see here, for example, we have the gap for the ventilator. Also, we have for the input-output interfaces. Then also we have here for the LCD screen or the touch screen. So in all of those places, a gasket must be used. Also here, some other applications can be when we have a cable and then we want to have a good grounding connection to the enclosure. Then we can have a gasket that can be cutted or customized to the shape of the connectors. And then we ensure that we have a good connection, a good grounding connection in this case. And then also another really common application is that with all the EMC chambers that you probably have already visited, if you check out the frames from the enclosure, you can see some metallic gaskets over it, just to ensure that the door from the EMC chamber is well connected to the frame or to the chassis in this case. Then about why gaskets are being needed, that probably will be one of the questions that you will have now in your mind. And the end gaskets are needed just to fill gaps. So because whenever we have our cover and then our enclosure, even if we think that the surface is super smooth without any kind of discontinuity or is like super soft to the touch, if you take a microscope and then you zoom it, you will find all the time like this kind of discontinuities all the time. And then these kind of discontinuities could provoke an electromagnetic field here, because at the end you will have some conductive surface, here another one, and then a current can go through it. And also at the same time, like the noise can go outside through it. So then what you want to use in this case, it is an EMC gasket, mainly just to fill the gaps. And then if you fill the gaps, then you are 100% sure that you are just creating your perfect Faraday box, which is also at the end the main purpose from your enclosure. Then in order to use correctly an EMC gasket, there is actually a general rule of thumb for all the mechanical shielding materials or grounding connection, or in this case materials, which is that in order to achieve the best conductivity value and then also at the same time to don't overstress the material from a mechanical point of view, the best thing is to compress the material around a 20 or a 30%. That's like a general rule of thumb. And then what you are achieving in this case is that, for example, there is the case for the conductive fabric over foam gaskets, where normally they are being produced with a non-conductive adhesive tape on the bottom. So then, at the same time, if you compress them at 20%, you will achieve the best value of conductivity, and also at the same time, you will make the conductive fabric, in this case, to overlap the non-conductive adhesive, ensuring that you will have a good connection between the top face and the bottom face. Then another extra tip in order to place them correctly into your enclosure is that you need to create, the best way will be to create a groove along the surface that is in the inside surface, or like in the inside side, sorry. And then the best thing will be to create a groove with a depth that it will be around 80% from the total height of the gasket, because then our goal will be to say like, okay, so I need to use a gasket that is 10 millimeters of height. So then in this case, the groove is going to have a depth, so a height in this case of 8 millimeters. So then I'm 100% sure that the 20%, so 2 millimeters more or less, they will be like in the outside. And then once I'm compressing the cover against the gasket and also against the enclosure or against the frame, I will be sure that I will get the best value. I will make sure that the conductive fabric will be overlapping, in this case, the non-conductive adhesive tape. And then at the same time, I will keep, or I won't stress in this case, the product. Also, another important tip is to put it in the inside, as I commented before, mainly because once you are, let's say, tidying it up or just adding or just compressing it, then you are sure that the force is being applied here. So then the gasket is being compressed, because if you place it in the other side, like in the outside wall, then what it may happen is that the frame, no, the cover in this case, will be bended, but not in a horizontal degree. It will be bended or tilted a bit. And then also the groove, it is quite important, so then the gasket doesn't slip out from it. So then you know that it is fixed in the same place. At the same time, another important tip is to don't use any kind of grease or like lubricant in this case, just to make like the compression from the gasket to don't scrap the walls or to don't get stuck. Because then what you are provoking is that you are adding a liquid or like something that is not controlled to the environment of the gasket, and then that could provoke some corrosion in this case. Another important thing to have in our mindset when we are using EMC gasket in our enclosure at the end is the material matching. Because at the end, I always like to think about it like it is like finding the perfect partner. Because at the end, if you don't find a good match for your material in this case, or like for your couple, then at the end, what you are provoking is that you will have problems in the long run. Which in the case about speaking about materials, what will provoke in this case will be oxidation layers all over the place. So that means that, for example, if my frame is made of aluminum, then the best thing would be to choose a gasket made of aluminum. And, or in the worst case scenario, choose something that is made of zinc, cadmium, steel, or magnesium. Because, for example, some common problems that designers or mechanical designers or engineers face many times is that they make the chassis made of aluminum because it is cheap, it is light, and also it doesn't add too much value to the mix. And then they use some conductive fabric gaskets, which they are made of nickel copper wires. So then that means that they are using aluminum and they are making contact with nickel, meaning that in 1 or 2 years, depending on the environmental conditions, they face oxidation layers over it. So that's a big issue and also a common one that can be faced or can be solved just by using an aluminum gasket in this case. Then, as I was commenting before also, there are several types of gaskets that they are being used for specific applications or for some specific conditions. Like, for example, the conductive elastomer gaskets, they are made of rubber, so they are the best ones for, let's say, for salty or humid environments. Then, for example, we have the contact strap gasket or metal gaskets at the end, which they are the best when you need a constant value of conductivity because it is just a beryllium copper stripe of it. And then we have the well-known conductive fabric cover foam gasket, which at the end it is a well-around gasket that it can be used almost everywhere. And then we have the knitted wire mesh gasket, which at the end it is a wire mesh that it can break through the oxidation layers because of the force or the resistance from the wire. And I know this can be a lot of information, and then it can be a bit tricky to know when to use a specific gasket and so on. So then that's why we created a kind of a cheat sheet, which at the end it can be used like a guideline or let's say like a checklist for choosing the correct gasket. Say like, for example, okay, so let's say that here you will find at the beginning like the most important parameters that normally they are being checked, that they are the ingress protection value, the temperature range, how you need to attach it to your enclosure, and also like more or less how much compression force you need to use it, if too much or too less. So then by using this table, for example, you can already start to discard it. So it will be like doing a shopping list at the end. Saying like, okay, so my application, let's say that needs an IP54 or more ingress protection value to avoid like some kind of particles to go into the inside, like dust, waters, or whatever. So then you can already discard this one and this one. But then if your application requires to be working at 100 degrees because it is related to automotive, for example, then you know that the conductive fabric cover from gaskets, so this one, it is already out of the equation because it can only work up to 85 degrees. So then that means that the only good choice, let's say, it will be this one. So this cheat sheet is already in our website, so feel free just to use it and download it, and also to give us feedback about it, to involve it. Then the next product group that I'm going to start to talk about, it will be the board level shielding product group. And then here actually in the board level shielding, it is the products from shielding that they are being used on PCB. And then here, let's say that we have two really big groups. The first one, it will be for improving your shielding from your PCB or from your application by using grounding or by improving your grounding connection. And then the other one, it is mostly about shielding like some specific areas from your PCB. Then, as I was saying, for the grounding, normally you will be able to find contact springs or contact fingers. So they have several names, but at the end is an elastic piece of beryllium copper with some plating over it And then also, since a couple of years ago, you are able to find some SMT gaskets on the market also. And then for the sealing point of view, the most popular solution at the end for board level sealing, it is sealing cabinets, sealing cans, or just at the end it is creating a small Faraday box, as I will explain later. Then, in order to choose, let's say, the correct grounding contact in this case, the first thing that you need to bear in mind is from where the connection is going to make, or it will happen. So because at the end, if, for example, the connection is going to be from an horizontal point of view, then you cannot choose some contact fingers in this case or some contact springs because of the shape of it. And then if it is from the horizontal point of view, then you have some other places or you have some other solutions. And then the second most important thing that you need to bear in mind, it will be the recommended working height. Because as I commented before, for the gasket, more or less, the rule of thumb is that for all the mechanical or elastic components from sealing, normally you need to compress them around 20, 30%. So then that means that if a component, it is 10 millimeters of height, the working height won't be 10 millimeters. It will be something between 8 millimeters and 7 millimeters. So that's something that you need to bear in mind. So to think about, okay, I need to use something that is a bit smaller, or you need to have this measurement in your mind. And then also at the same time will be something that will affect directly their working height. It is the compression force. Because depending on the material that you're using or the type of product that you're using, then you will have to use maybe a contact finger or an SMT gasket. Just as a general rule, SMT gasket normally they require less force than contact fingers, maybe because of the foam material that is in the inside. At the same time, like I was saying for the gaskets, something that you need also to have in your mind for selecting the correct product, it is the materials. Because at the end, you will have two different materials making contact. Because, for example, you can make contact between your PCB to your enclosure. So then, the best way, let's say again that our enclosure is made of aluminum, so then the best thing would be to use maybe some tin material or some nickel material, and also to avoid nickel material over it. So, for example, let's say that also, so maybe now it is not the best example, but let's say that we want to make some contact between our copper pad with a contact finger. Then in this case, using a contact finger made of nickel material can help with the corrosion that will happen on the pad. So then in this case, for example, using this kind of plating will help. But then we know that nickel, it is a bit tricky to solder it. So then in this case, what we have been done, or what we have been doing with our contact fingers made of nickel, it is to add a layer of tin into the bottom. So then it is also easy to solder it. But anyway, think about the materials when you're going to choose your product. Because also most of these products, they can be customized, the plating can be changed, also the shape. So it's something that it can be workable. Then speaking about the second product group, that is the sealing product group, let's say for board level sealing. At the end, when you're having a sealing cabinet, what you want to create, it is a small Faraday box into your PCB or inside your PCB to, let's say, improve one area or one specific area. So here actually the sealing cabinets can be used for two different points of views at the end. So for example, you can use it in order to shield or to encapsulate a noisy area. So then let's say that this IC here is just radiating or just creating a lot of EMI. So here in this case, if you use a sealing cabinet over it, you can just keep all the noise in the inside, but then also they can be used in the other way around. Meaning that, okay, I have this IC that is really sensible to external noise. So then you can just seal it and then you can protect it from the outside. So this is what I meant that they can be used from two different points of views. Then speaking about cabinets, actually they are currently in the market. There are two different types, or there are two big groups. Once it is the most traditional and standard solutions, which are the ones here on the left. And here, as you can see, we like to name them traditional or standard because of how we produce them. That at the end is that we work the material, meaning that first we cut the metal sheet in this case, and then we are just bending it and pushing it until giving the shape that we want. That means that on the corners, for example, we have some tiny apertures that at the end, they can be a door in order for the noise in the inside to go to the outside or the other way around. So the noise from the outside to go to the inside, meaning that these cabinets, they are mainly fitted for low frequency applications. And in this case, for low frequency applications, I mainly mean the like from 5 gigas to the bottom. So from 5 gigas to 1 giga or even lower. This is the application that really will fit this kind of cabinets. And then for the new technologies that they are coming now, like for example, 5G, EOT, or even frequencies higher or above 5G, then there is also a new type of cabinet, which is totally seamless because the way that it is being produced, and it totally fits for high frequency applications, mainly because there is no kind of gap or tiny aperture or hole where the noise can go to the outside or the noise can go into the inside. So everything is just kept in the inside. As I commented, the seamless cabinet, it is the best one for 5G applications or even high, or for the new high frequency applications, mainly because of how they are being produced. Mainly because we are producing, or they are being produced by deep drawing technology, which at the end is that we get the mold from the cabinet and then we're just pushing the material really down or really slowly to the bottom of the tooling. So then we have the desired shape. And then here you have a simulation that we have done in the past in order to prove that what we are saying all the time it is true about one it is mostly for low frequency and the other one is for high frequency. So just to explain a bit more this simulation that you can see here. So on the left here we have the simulation for a signal at 8 gigas. So here in the inside we have a microstrip line, and then this microstrip line is being, let's say, it has a signal that it is at 8 gigahertz. And then as you can see here, there is a lot of noise just coming outside of it through the pads or through the tiny holes that we have here. And then on the left, we have exactly the same PCB. So the microstrip line being here with the same signal at 8 gigahertz, but then with a cabinet that it is totally seamless. So with this kind of technology. And then as you can see here, all the noise that it is in the outside or it was in the outside, it is being kept in the inside, and then nothing is coming outside. So then let's say that you can use, and so then you can use this application or you can use this cabinet for this frequency range in case that you want to keep everything in the inside or you want to protect the things from the inside. Then another common problem here is that most of the times at the end cabinets, they are a metallic component, and then when they are exposed to salty environments or to humid environments, then they can get corrosion. So in this case, once the cabinet is being soldered, and then you have the 360-degree low conductivity connection to it, so you have a conductive material all around the area, then the corrosion or the oxidation layer in this case, it won't affect to the sealing performance of the product in this case, because at the end you will have already, let's say, the low conductivity sealed around the area. And then it will only provoke problems when actually the corrosion eats the material and then you have gaps over it. But then you will need to wait for thousands of years in order to have it. But anyway, as a designers, we understand that maybe having some corrosion into your PCB or into the end application doesn't look good, especially for the end customer, because at the end you're paying some money for it. So you want to have something that is shiny and also it looks really nice. So then for those kind of situations, there is the alternative to do a sealing cabinet, but made of nickel silver, which at the end, the sealing performance is one-on-one almost the same. And then once it faces a humid environment or a salty environment, it remains the same. So it has a higher degree of resistance against, in this case, salty or humid environments. And then another important thing is that, please, I'm asking you from a, let's say, designer point of view in this case, which is bear in mind that if you use or if you think to use a sealing cabinet from the beginning and then on your PCB you already include the footprint or you reserve the area for the cabinet, or you just leaving the area for it for free or just leaving the footprint, you will save a lot of cost in the future. Because it has been many times where we face the situations that when the customer, or in this case, you, the designer, you're already on the EMC lab. And then once you are over there, then you realize that you need to use a cabinet. And then in order to don't rework the whole PCB because you're already on mass production or something like that, then you are asking to produce some customized or some specific application with some specific measurements for a ceiling cabinet. And cost-wise, it is you will save a lot of money, a lot of headaches, and also a lot of time just by including it from the beginning and thinking to use one of the standard dimensions from the beginning than requesting a customized solution at the end, mainly because of a matter of time and a matter of cost. So in this case, for example, in our case, we have already more than 260 different dimensions. So please, the next time that you're going to use it, I will recommend you to double check them and then to try to use one of our standard dimensions instead of a customized solution. And last but not least, also, we know that many times when if at the end you need a specific solution because the shape of the PCB is out of the standard or you need to cover one specific area, we know and we understand that many times asking for some prototype samples, it can be a bit tricky at the end, or it can have some extra cost that they are not really big fan from the, in this case, accounting department. So then in those cases, what we have available in this case, it is the shielding, in the shield do-it-yourself solution, which at the end it is a piece of nickel silver material, which can be used that you can bend, you can cut it, and at the end it will be like a kind of a Lego that you can create your own cabinet. And then with that one, you can solder it to your PCB, or you can solder to the PCB the shielding cabinet clips, or like some clips, and then you can just attach it the cabinet to your PCB. And then after it, you can just try it. So it is reworkable or removable. So you can just use it or you can just place it and then just unplug it. And now the last product group that we are going to speak about, it is in this case the magnetic absorbers. So magnetic absorbers, normally they are being used in order to clean the noise from the PCB traces, like you have here some signal or some data lines, and then you have some crosstalking or you have some resonances into the line, and then you can use them to filter them. When on the PCB, you don't have enough space to use some more passive components in order to clean the trace of the signal. Then also another application, it is just to eat or remove the noise that you could have on the environment. In this case, by just attaching the absorber sheet into the enclosure, for example, and then just it will act like a kind of an exponge that it will be absorbing the noise from the environment slowly. Then, last but not least, what we have on the market or what you can find on the market. So actually, there are two different types of magnetic absorbers. The first one, it will be the flexible absorber sheets, or the acronym can be founded as a FIS. And then this one, at the end, it is a mix between ferrite powder mixed with some silicon powder into it, or some silicon particles, sorry. Then that gives to the FIS, or to the absorber sheet, some magnetic properties. And then at the same time, it gives it flexibility. So then you can bend them and also you can just stick it in some other places. So at the end, it will be like kind of a sticker at the end. And then the other alternative or the other kind of product that we have in this case, it is, or that one that you can find on the market, it is the flexible sintered ferrite sheets, which at the end, it will be a sandwich of different layers of magnetic powder. And then everything is just being compressed and smashed like a really big sandwich. And then the perks and the cons from this kind of ferrite sheet at the end will be that it has a higher value of permeability than the flexible absorber sheets because you have ferrite layers all over the place all the time. But at the same time, the con is that it is not really flexible, meaning that just by bending them a bit, then you will be able to feel how the ferrite layers are being or are cracking all the time, meaning that at the end, the magnetic properties will change all the time. Then some common applications to use, in this case, the magnetic absorbers, is to solve problems about intra-decoupling or inter-decoupling, which at the end, intra-decoupling problems is that you have a component on the same level of the PCB, and then it will affect the neighbors. Like, for example, in this case, this IC is creating a field that it is affecting the other IC here. And then the inter-decoupling problems are the ones that they affect to let's say, the neighbor up or down the PCB. So when you have, for example, in this case, a rack of several PCBs or like a server or something like that, then over there, the most common problem will be the inter-decoupling. So one PCB will affect the other one, or one component of one PCB will affect the other one. So then by just sticking a layer of absorber sheet, maybe here, or maybe in this case, like just over the IC or just next to it, then you will be able to solve this issue. But then also magnetic absorbers are being used to optimize systems because of the properties that the ferrite has. So for example, for applications like NFC, RFID, or wireless power applications, then the ferrite can be used in this case in order to improve the communications in order to avoid the problems that the AD currents can provoke. So I'm not going to go too much into the physics of it because I'm actually running a bit out of time. So at the end, the AD currents, what they are doing is that they are shifting the waves from the wireless power system or from the NFC. And then by using a ferrite sheet just here in the middle, what you are doing is that you are just refocusing again the signal to the desired way. So then here, for example, it can be a nice application for the ferrite sheets. Then I have been speaking all the time about absorption, reflecting. So the summary is that the best way to know which magnetic absorber you need to use on every specific application on every time is to check the permeability, which at the end, the permeability, it is a material property. So that means that the thickness doesn't matter here. And then the permeability, normally it is being given in two different factors. So the mu prime that you can see here on the left, and then the mu double prime, which is on the right. And then the mu prime at the end gives you the value that it can give you an idea about how much the material can reflect or can redirect the magnetic field. Meanwhile, the absorption or the mu double prime will give you the capability of the material to absorb the noise from the environment, or in this case, the magnetic field. So by checking out or by comparing, in this case, the values for permeability, then you will be able to more or less have an idea of which type of absorber you need, if it is a FSFS or an FI, so a flexible absorber or a sintered ferrite. And then the best way to know which one you have to use will be to go to your sales colleague or to person of contact from Würth, ask for many samples, and then just try it into your system. Because at the end, there are several factors that will affect the performance of it. So the best way will be just to ask for samples and to try it. And then as a bonus track, recently there are many applications because of the new requirements that they are becoming, especially for dimensions wise, that there are applications that requires shielding, magnetic field or electric field, and also at the same time to have some thermal interface materials in the middle. So then that's why there is some magnetic absorber that they have some ferrite powder into it, silicon powder into it, just to give them also some flexibility. And then at the same time, it has some ceramic material embedded into the whole mixture, allowing it to transfer some heat. So for example, in our portfolio, you will be able to find the FIS thermal or thermally conductive. And then this material will help you just to transmit the heat, for example, from this IC to the heatsink. And then at the same time, it will be able to help you to mitigate all the EMI problems that you may have in this environment or in this application. So that was all from my side. So thanks a lot for joining the session, and I hope that you have too many questions for me.
Yeah, thank you, Victor, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation today. Then you can download it on the right side on the black button. So then I think we can start with the Q&A session. Victor, are you ready for the questions?
Yep.
Cool.
So, I mean, well, just before starting with the questions, I mean, there is some event that we are going to help in Munich in the 14th of May, I think it is, which is the EMC days. So this is mostly just like a short reminder to everyone who is around Germany or like in the south of Germany, just to pop up over there and then just pass by the EMC days over there. So I'm sorry for interrupting.
Everything good, everything good. More information about that you can find on the website, on our teams, on our event list. Sorry. So now we can start with the questions. First question, what does the abbreviation BLS mean?
So at the end, BLS, it stands for board level shielding in this case. So, and then you can understand it as any kind of shielding component that goes over the PCB.
Thank you. Then next question. It's a question about the slide 25.
Okay.
The question was low frequency range and high frequency range. He will know, what is the low frequency range and what is the high frequency range.
Yeah. So I think it is the previous slide to the one that we are currently showing. No, so it has to be a bit more. So it has to be the 25, where we saw the standard solution versus the seamless solution. So it has to be around 1, 2, 3. One more? One extra more? Yeah, that one. No, exactly that one. So at the end, so let's say that the main issue or like the main purpose about when to use one or on another one, it is at the end that the standard solution, so that one that is for low frequency, which is the one that you have on your left, and then I have all on my right here. At the end, this one, it is mainly for applications that require some shielding between, let's say, couple kilohertz or couple megahertz until more or less 5 gigas. Then from 5 gigas above, it is when we recommend to use the seamless solution in this case.
Thank you. Then next question. It's also a question for page 27.
Okay.
Which simulation tool was used for the simulation?
Yeah, so in our case, we made the simulations with ANSYS because also like all our components they are already implemented on the material library from ANSYS. But then probably also when I was checking out before the chat, so they also offered like some other tools, like in this case CDT. So, but in this case, our simulation was done by ANSYS.
Okay, thank you. Then next question. How can I measure and guarantee the shielding effectiveness? Yeah.
So at the end, the shielding effectiveness can be measured in several ways. That's why, for example, if you make a quick research on IEEE Explorer, then you will find out like thousands of papers about how to measure it. The thing is that in whatever you see on the datasheet about the saying like you will have 5 dBs of shielding effectiveness, those 5 dBs are based on the standard. So here the best thing will be to use those kind of charts or those kind of measurements mainly as a kind of a reference. So then you know like, okay, so this material more or less will give me this value and then I can use it on my application. That's the best way in order to say to do it. And how to measure it is just to grab the standard and then just to measure it on your application at the end.
Okay, thank you. Then next question. What is the frequency limit for standard BLS types?
So that probably I'm going to say this many times during the Q&A, that is, it depends. So if we are talking about shielding cabinets, as I commented before, if it is for the traditionals, let's say that the limit, it is around 5 gigas. If it is for the seamless cabinet, then you can go easily 50 gigas or even a bit higher. At the end, it fully depends about how, let's say, the component will react in the whole environment. And then with the whole environment, I mean like the rest of the PCB, the enclosure, and everything. So sadly, there is not, let's say, a definitive answer here. And then if it is regarding the contact fingers and also the SMT gaskets, at the end, they are mainly used for grounding. So frequency limit, it is not a big factor here.
Okay, thank you. Then next question. Which components are, from your experience, the most commonly shielded component at board level? Power, ICs, and so on.
Mm-hmm. So in this case, the straightforward answer is the ICs. Normally, they are like the more sensible ones and also the ones that they tend to get into more troubles most of the times. But then also some clocks also, they tend to have or to get into trouble most of the times. And also that's why normally you will be able to find them like the clock on the PCB, plus then also with a shielding cabinet over it. So in my case, or based on my experience, those will be the most common sensors, or even more, the modules for Bluetooth, Wi-Fi, and everything.
Okay, thank you. Then I think one last question. Shielding cabinets can be modified from the standard. If that's the case, what can be done?
Yeah, so shielding cabinets can be modified from the standard, let's say, specs or dimensions. But like I said on the presentation, I don't fully recommend it because at the end, let's say like time-wise, it will be a lot of time consuming. But then just going back to the question about what can be modified, for example, material can be changed, dimensions can be changed also at the same time. Also, how you attach them, or let's say the method or the type of cabinet also can be changed. If it is a one-piece solution or a two-piece solution, where you have the frame plus the cover. Then also some compartments or like some sections inside of the cabinet also can be done. At the end, you can think about this as it is a piece of metal, and then the metal can be worked as you want. The only thing is that the more complicated shapes that you want, the more time that it will require, or the more resources that it will need.
Okay, perfect. Thank you. Then I would say we are finished with the session. All the questions we not answered now. Victor will answer them via email in the next days. So now, thank you, Victor, for all your answers and for the interesting presentation. Now, thank you for your attention. I hope you enjoyed it, and hopefully we see us in the next session of the Digital Redays. And I would say thank you and goodbye.